Welcome, friends. Today we'll see how to calculate the greenhouse gases for the iron and steel production. Myself, Dr. Atul Dhale, professor in Production Engineering Department from DJ Sangvi College of Engineering, Vile Parle, Mumbai University. The first video, it was on the environmental aspects and just the introduction of the what are the different aspects of the environment. Then the second video, it was related to what are the industrial environmental performance matrix for manufacturing industry and the ISO standards for manufacturing system and precision manufacturing engineering. Now, what are the outcomes of this videos? After learning through the video, the students will understand about the environmental aspect and impact of development activities of human being. Second, understand the different industrial environmental performance matrix and manufacturing industry and apply the ISO standard for manufacturing system and precision manufacturing engineering. And the third one, apply the ISO standards and analyze the greenhouse gases emission for iron and steel production. Now, before going into details, the first we should know, you must have heard the term carbon footprint and the greenhouse gases. The first, what do you mean by the carbon footprint? Suppose if I ask you which cost is more, whether the cost of the 1 kilo of strawberries or a stick, or which is more expensive, like a can of a beer or a bottle of a shampoo, we can easily give the answer for this in terms of rupees, dollars or euros. But if I ask you, what is the cost of the product in grams of carbon dioxide? This is somewhat difficult answer because in general, normal public doesn't know how to calculate a carbon footprint, or in this cost what includes exactly. So let's take an example of bottle of shampoo. So when we are calculating the cost of the gram of carbon dioxide, whether we should include the greenhouse gases involved in the production of plastic packaging, because the bottle which we are using for the shampoo, it is of the plastic. Then over that bottle there is one film wrap over it. So plastic film used to wrap the bottles, whether we should consider that. When they are transported on a pallet, whether that cost you have to consider, the ingredients in the shampoo itself, and even the energy used to heat the water for the shower. For all these activities, definitely there is a carbon emission, and so we have to consider this. Now, other than this also, there are a number of activities involved related to this small bottle of the shampoo. So definitely the person to person, this result will vary, right? So therefore, for uniformity, the ISO has specified the ISO standard, that is ISO TS 14067. So this ISO standard, it is revised and it constitutes of the reduction in the scope as follows. The ISO 1426, this includes the principle, requirement and the guidance on communication of the carbon footprint of a product, and the partial carbon footprint are now covered. The ISO 140643, here principles, requirements and guidance on verification are now covered. ISO TS 14024, principle, requirement and guidance for partial carbon, PCR are now covered. The ISO 14064, the requirements for the treatment of biogenic carbon and electricity have been revised and clarified. This document is a generic standard for quantification of the carbon footprint of the product. Again, this ISO 1460, this family provides the clarity and consistency for quantifying, monitoring, reporting, and validating or verifying the greenhouse gases emission and removals to support the sustainable development through a low carbon economy. Specifically, the use of the ISO 1416 family enhances the environmental integrity of the GHG quantification, enhances the credibility, consistency, and transparency of the greenhouse gases quantification, monitoring, reporting, validation, and verification. This also facilitates the development and implementation of GHG management strategies and the plan, facilitates the development and implementation of mitigation action through the emission reduction or removal enhancement. This also facilitates the ability to track the performance and the progress in the reduction of the greenhouse gas emission and increase in the greenhouse gas removal. Also, there are some standard ISO 1464-1 detailed principle and requirement for the designing, developing, managing and reporting organization level. Then ISO 14064, this gives you to the details principle and the requirement of determining the baseline and for monitoring, quantifying and reporting the project emission. It provides the basis for the greenhouse gas project to be validated and verified. The ISO 14063, this gives the requirement for verifying the greenhouse gases statements related to the greenhouse gases inventories, greenhouse gases project and carbon footprints of the products. It describes the process for the validation or verification including the variation. This slide also shows the ISO 1465. This defines the requirement of the bodies and this description. Then the 1466 and ISO TR 1469. This assists the users in the application of the ISO 14641, providing the guidelines and examples for improving the transparency in the quantification of emission and their reporting. It does not provide the additional guidelines for the 641. And here in this slide you can see the complete relationship among the ISO 1460 family of the GHG standard. It is given, you can see here. Here it is 1465, 1466 and here 1464, 64.1, 64.2 and 67. This all are related and finally you will get the GHG statement. Again, beyond this, the relationship between these documents and standard beyond the greenhouse gases management family of the standard, you can see here this ISO 14067. This is the carbon footprint study report, then communicate to this footprint communication, and here from this standard ISO 1426, 44 and 71 you are getting the input, and if there is no communication then it goes. So this is the relationship between the document and the standards. Now then, as we heard the name greenhouse gases. Now, what is exactly the greenhouse gases? The gases constitute of the atmosphere, both natural and anthropogenic, that absorbs and emits the radiation at specific wavelength within the spectrum of the infrared radiation emitted by the Earth's surface and the atmosphere and the clouds. In this, the most significant greenhouse gases are water vapor, carbon dioxide, methane, CH4, and the nitrous oxide, N2O. According to Environmental Protection Agency, the oxygen is the second most abundant gas in the atmosphere, which does not absorb the thermal infrared radiation. Now, there are some statistics here. In this slide here, year on year growth of CO2 emission by the different sectors. So from these slides, you will come to know why I chose this iron and steel production sector. You can see here in this slide the impact of this iron and steel sector is the most one, almost you can see from 2005 to 2013, almost there is a 40%, 40 to 50% contribution of the growth of CO2 emission by this iron and steel gas. Even here some statistics given, emission from the top 15 for the year 2013 in India. You can see the Gujarat is the most dominant state where there is a emission in million tons, which is the maximum. Then there comes the Odisha, Chhattisgarh, Jharkhand, Karnataka, Maharashtra, and you can see the least one is the Telangana, Haryana, and Uttarakhand. You can see here again the trend in overall manufacturing industries. Again from 2006 to almost 2013, this is the emission per capita. The red curve shows the emission per capita and the blue curve shows the emission per unit GDP. So this also shows that it goes on increasing up to 13. Then here the overall carbon dioxide equivalent emission due to various fuels used within the manufacturing industry, and you can see the most dominant fuel, it is the coal, and second one is the fuel gases. But the coal, it is the most dominant fuel by which there is a CO2 emission is very high, and in 2013 you can see it goes on increasing. Again here in this slide also there are number of different sectoral emission is given from 2005 to 2000, and this was all the information, it is from the source CEEW analysis. So here also you can see almost the 40 to 50% iron and steel production is dominant. So emission from the iron and steel industry alone accounts for roughly 45 to 50, while emission from the non-metallic minerals industry contributes to around 20% of the total emission. That means even the chemical industries, cement industries, that contributes less emission of CO2. And that's why we have taken this topic, which is the iron and steel production. Now this is related only to the production of the steel. I have not considered the calculation of the other part. We'll discuss later. In iron and steel tool provides the two different methods for calculating the CO2 emission. One method requires the data on the quantities of reducing agent and blast furnace additives used, as well as the quantities of the carbonate fluxes introduced into the furnace. And the second one, the alternative method, requires the data on the amount of iron or steel produced as well as the carbonate fluxes. So here first we'll try to understand what exactly how this iron and steel production happen. You can see this, there is a iron ore, it goes to the direct produces, here it is the solid metallic iron. This ore, there is a coal injection, coal, and the coke oven, and then the limestone. Now this goes to the blast furnace. Then the pig iron casting, this is one part of through this blast furnace, and another one is the basic oxygen furnace, some part of this which goes to this oxygen furnace. Then recycled steel will goes here in the electric arc furnace, and then steel refining facility, and then after that it will the continuous casting, and you will get the slabs or some thick slabs, thin slabs, or this blooms or bleeds as per the requirement. Now, if you see the schematic diagram, in schematic diagram you will come to know the coking coal, carbon breeze, iron and additives, and coal injection. And this is the blast furnace where CO2, CH4, NO2 will produce. Now, then this, as I told you, this pig iron for iron processing, this will go, and the steel making. So there are, and from this you can see here, this is the coke plant, coke oven gases, and these are the CO2, CH4 and N2O. These are the gases which produce. So this figure shows the greenhouse gases emission sources associated with the iron and steel production that are considered, right? Other sources that are not represented here and that they contribute significantly to the facilities overall emission include the on-site transportation of material and the consumption of the purchase electricity, heat and steam. That part is not considered because you will come to know that only the greenhouse gases related to the iron and steel, it is a very big and vast topic. So now we need to understand what is the tires. So generally they there are three tires: tire 1, tire 2 and tire 3. And this tire 1, tire 2, tire 3, if it goes on increasing this number 1, 2, 3 towards 3, the value become more specific to the reporting company, leading to a greater accuracy. That means in tire 3 the values are more specific and the accurate one. Now tire 1, we'll see one by one. Tire 1 methods estimate the emission by multiplying the production data such as volume of fuel use or the steel produced by the industry specific default emission factor. So tire 1 defaults are supplied for all of the methods in the iron and steel wherever appropriate. Now this is the global one, right? So globally whatever it is accepted, we are accepting that value. In tire 2 the method requires the data that are less general. It is not general, it is specific. It may be related to the local one also. So for instance, the tire 2 emission factor might reflect the typical industrial practices within a specific country, right? Whereas a tire 1 factor constitutes a global default value. So facility specific data are not considered. Tire 2 data might be available from the national statistical agencies or industry associations. And tire 3 methods required the facility specific data such as the composition of the fuel combusted at a facility or the specific type of technologies employed at the facility. Now, when we are calculating the CO2 and CH4, there is a difference. Now, which type of difference it is? The CO2 emissions are largely determined by the carbon contents of the consumed material. Also, the CO2 emissions are best determined using the material balance approach that tracks the flow of carbon through the industrial processes. Whereas N2O and CH4 emissions are much more influenced by the combustion or emission control technologies employed by the industrial apparatus, right? So this is depend on the which type of technology we are using, which type of apparatus you are using. So N2O, that means nitrous oxide, and the methane CH4 emissions are best determined using the equipment or the process specific emission. Also, this N2O especially is only considered by the tool in relation to the stationary combustion sources. This is because the N2O emission from the industrial processes specific to the iron and steel sector are assumed to be negligible. So in iron and steel production, so basically there are three parts, or you can say the stages: stationary combustion, industrial process emission, and the limestone and dolomite production. Under this stationary combustion sources, there are four main types. Electricity generation, for example, the capitative power plant boilers. Then the reheating furnaces, other coal and oil use, example, meal sections. Then the coke production, and the fourth one is the flaring. This covers under the stationary combustion. Then the second one is the industrial process emission. Again, there are four parts. The four main sources that contributes the process of greenhouse gas emissions are sinter making, peltzing, iron and steel making, and direct reduced iron production. And the third one is the limestone and dolomite production. We'll see this, how to calculate the CO2 under this different sections, CO2 and of course the CH4. So emission from the electricity generation and the reheating furnaces. You can see the CO2, first fuel consumption data. So we'll use this equation one, the total annual fuel consumption, it is equal to the annual fuel purchase minus the annual fuel sale plus the fuel stock at the beginning of the year minus the fuel stock at the end of the year. And the fuel carbon content and the heating values, here this equation gives you the LHV, LHV means lower heating value, that is equal to the HHV, the higher heating value, minus 0.0212H minus 0.245M minus 0.008Y. Here this M is the percentage of the moisture, H is the percentage of the hydrogen, and Y is the percentage of the oxygen. Then the carbon content factors can be converted to an energy scale using the heating values with the equation 3. So here the converting the carbon content factors from a mass or volume basis to an energy basis. So by this equation we can FCH, it is equal to FC divided by HVF. So this FGS means the carbon content of the fuel on a heating value basis. FC, it is the carbon content of the fuel on a mass or volume basis. Example, the short ton carbon divided by the short ton, and HV means heating value of the fuel, right? So all this data, it is available. So you have to take that data, substitute, and you can calculate. Then calculating the CO2 emission. So calculating the CO2 emission using carbon content data that are expressed on a mass or volume basis. You can see that there are two equations, mass basis and the volume basis. So here this AFV represent the volume of the fuel consumed, and AFM in second equation volume basis, that represent the mass of the fuel consumed. So 14 divided by 12, that is the ratio of the molecular weight of the carbon to that of the CO2. So all these abbreviations it is given here. So by this equation you can calculate the CO2 emission. Then the calculating the CO2 emission from stationary combustion sources using the carbon content data expressed on an energy basis. So where E, it is the amount of CO2 emitted, A, it is the mass of the fuel consumed, HVF, it is the heating value of the fuel, FCH, carbon content, FOX, fraction oxidation factor, and 14 by 2, it is again the molecular weight of the carbon to that of the CO2. Then how to calculate the CH4 and N2O emissions. The calculating the N2O and CH4 emissions for the stationary combustion sources. So this is according to the tier 1 and tier 3. According to tier 1, it is equal to AF HHVF into. Now this I want to tell you again one thing, that HHVF and HHV and LHV. LHV, it is the lower heating value. Now lower heating value means the net calorific value, and the HHV, higher heating value, means the gross calorific value. So here E is the amount of either N2O or CH4 emitted. Then AF, it is the amount of fuel combusted on a mass or volume basis. AF, it is the Tier 1 fuel specific emission factor. This is given in the further slide. I have given the one table in which we can, these values are available. And this is ESEF, this is the Tier 3 equipment specific emission factor. So this is available in table 1. You can see here in this table 1, all these factors are given here according to the fuels, whether it is liquid fuel, then residual fuel or gas fuel, then solid fuel, natural gas, and accordingly, see the LHV or NCV, net calorific value, this values you are getting, and this is the standard value, right? So from this you can select the value, you can substitute in that equation, and you will get the CO2. Then the emission from the coke making or coke production. Now here, first you have to see whether the offsite coke production facility owned or controlled by the third party, or it is produced by the industry itself. So there may be two cases. So one is, you can see here in this scope 1, here it is written, the emission from the coke manufacturing facilities included within the organizational boundaries of the reporting company, or the scope 3 is the emission from the third party facility. That means coke, whether you are manufacturing itself or it is from the outside, and accordingly we have to calculate it. Now you can see the equation 7 gives you the calculating CO2 emission from the on-site coke production. So there is this big equation, Cc into C suffix Cc plus summation of Pm into CO plus Bg into Cbg minus CO into CCO minus COG into COG, and all these factors. So you can see here the Cc, it is the quantity of the coking coal consumed. So in this slide, all the details are given about these factors. You can substitute the value and you will get the emission of CO2 from the on-site coke production in the tons. If it is offsite, then the calculating CO2 emission from the offsite coke production. So for that you have to use this equation. So by this equation you can calculate the CO2 emission for the offsite. And this carbon content, especially, so you can see here in this equation, Cx, carbon content of the material input or output x ton. So here in this equation you can see this Cb. So this is this you have to calculate. So this Cx, this part, this is available in this table. So definitely you can select the value from this and you can substitute these values in the equation and you can calculate the CO2 emission. Then the next, it is the CH4 emission from the coke manufacturing can be calculated using the equation 9, regardless of whether the coke was produced outside of on-site or off-site. So calculating CH4 emission from the coke production, you can use this equation. The CH4 ECH4, it is equal to EF CH4 coke. So emission from the flaring, you can calculate this by this equation, CO2 emission, it is equal to Q into 5.16 into 10 raised to power minus 5 into C mole axis, right? So by this equation, then CH4, calculating the CH4 emission from the flares. So by this equation, you can calculate this CH4 emission. So Q Fg into 3.83 into 10 raised to power minus 7 into CH4 mole ratio into GW. So by this equation, you can calculate the CH4 for the flaring. So this is the first part, that is for the stationary one. Then the second one is the industrial process emission. So sinter production, the CO2 emission should be calculated following equation this 12. So by this equation, you can calculate the CO2 emission from the sinter production. Then the iron and steel production, this CO2 emission from the iron and steel making can be calculated by using the equation number 30, which is given here. This is the big equation. You can see this. These are the different elements involved in this equation, and you have to substitute the values which is available in the data. So direct reduce and iron production. So for this, you can use this equation, ECO2 into dr into 14 by 12. So by this, you can calculate the CO2 emission from direct reduce iron production, right? Then CH4 methods for the processes sources. So calculating CH4 emission for sintered, before this we have seen the calculation of CO2. Now for all these three, calculation of CH4 emission by the sinter production, you can use this equation. From the pig iron production, you can use this equation, and from the direct reduction iron produce, you can use this equation, right? So these are the values which we required. So emission factor you required here, you can see this EFX, this is the emission factor. So emission factor for the sintered production or DRI, it is different, so you can take the value and you can substitute it. And then lastly, the limestone and dolomite production. So calculating the scope of, now here there is a two ways. The scope 1 emission, calculating the scope 1 is CO2 emission from the production. So you can use this equation as we have seen previously. Then the tier 1 emission factor for the carbon carbonate species. So here in this equation, you can see here, you required here the emission factor for the carbonate, right? So that factor, emission factor, you are getting from this table. You can substitute and you can calculate. Then the scope 3, it is for the offsite, calculating CO2 emission from the lime production. You can use this equation, and the deriving the custom CO2 emission factor for the scope 3 emission, you can use this equation. So these are the different tables and data available. These are the tier 1 default carbon content values and all. So in this 4-5 slides, I tried to show you what are the different values for different processes and all that is available. So that you can see here in the table 7, defaults of estimating the CH4 and N2O emission from the stationary combustion of the fuel. These all the values are available. This is the standard value which you have to pick and substitute. Then the unit conversion ratio, because in different countries we use the different units. Then now the most important part, it is the sustainability of the iron and the steel production. The India has had the benefit of adopting the latest. Why? Because still there is a development stage. in India. So you can we can use here the latest clean and energy efficient technologies to make it transition to sustainable manufacturing. The India has added the advantage of the steel being a 100% recyclable product, which is fundamental to achieving a sustainable circular economy, where the society reduces the burden on the nature of creating a better life for everyone on the planet. The World Steel Association, the life cycle management report suggests that for every ton of steel scrap used to make a new steel, we save over 1400 kg of iron ore, 740 kg of the coal, and 120 kg of the limestone. So, remanufacturing plays the crucial role in the steel industry. Steel strength and durability enables the long product lifespan. Of course, on the average, the production of 1 ton of steel result in 200 to 400 kg of byproducts. This includes the slag, dust, sludge, and other material. Today, these byproducts are an integral part of the business, and its recycling provides the significant benefits like the reduction of the landfill waste, decrease in carbon dioxide emission, and preservation of the natural capital. The steel industry has invested in research and technology to create a new grades of advanced and ultra high strength of the products. Over time, this has helped to reduce the energy consumption per ton by 60% and weight of many steel applications by 40% over the time. And with improved technology and adoption of the global best practices, the steel industry has considerably reduced its environmental footprint, and so it will be sustainable. Another important aspect of ensuring the sustainable manufacturing is reducing our water footprint. Water is used throughout the steel making process in the cooling operation for descaling and the dust scrubbing. Even though the steel industry uses the large quantity of water, every liter of that water is consumed and most of it is reused and returned to the sources. The global best practices such as the zero effluent discharge, the use of cyanide bacteria for the treatment of the wastewater in the plants, and on-site power generation is also being incorporated in the industry, and so the iron and steel production industry will become more sustainable. Thank you very much, friends.